For the polar representation of a vector, first thing I'm going to do is draw what is hopefully a very familiar looking drawing. Suppose that we have a vector. We'll make this a quadrant 1 vector for lack of a better idea. We'll draw this in terms of its components. We'll take vector A, and we'll refer to the components as A1 and A2. So vector A has components A1 and A2. Now with that in mind, suppose also that we find an angle in standard position associated with this. Now, vector A is represented in terms of its components A1 and A2. As we saw in our last example, though, it is possible to express A in terms of the sine and the cosine of each of these. This would be the magnitude of A times the cosine of theta, and this would be the magnitude of A times the sine of theta. The thing that this gives rise to, for those that are paying really close attention, is that this looks an awful lot like x is equal to r times the cosine of theta, x because it's the horizontal component, and this looks an awful lot like y equals r times the sine of theta, where r is the length of the hypotenuse, or in this case, the magnitude of the vector. This gives rise to what we call the polar representation of a vector. So A is equal to the magnitude of A times the direction vector associated with A. We'll call that U for a unit vector. In the example in our last video, we were dealing with the vector -2, 5. We were able to express the unit vector in that direction as -2 over the square root of 29 and 5 over the square root of 29. If we factor out that square root of 29, then we now have equality between these two vectors. So this would be the magnitude of the vector that we referred to as v times the unit vector pointing in that direction. It's much more common in the real world for a vector to be decomposed into these two things, a magnitude of the vector and a direction of the vector. For example, if somebody pulls me over for doing 55 miles an hour in a 45 zone eastbound on M59, they wouldn't say, oh, his velocity vector was 55, 0. They would say that he was traveling 55 miles per hour in an eastbound direction. Well, that's typically the way real-world vectors work, and so we're going to talk about how to translate between those two sorts of things.